ஒருவாட்டி ஆடியோ மட்டும் செக் பண்ணிக்கோங்க ஜூம்ல. இல்ல பாஸ்கர் வந்து ஜூம்ல ஆடியோ லாகின் பண்ணிட்டு செக் பண்ண சார். Guys, am I audible? Those who are online, am I audible?
Yes, sir.
Yes, sir.
Fine. Is the screen visible?
Yes, sir, visible.
Okay. Permission garage band. Check. Okay. Right. Record ada. Can you go back? Yeah. So shall we get started? Yeah. So to those who are online, shall we get started? Yeah.
Yes, sir.
So in the previous class, we saw the derivations that are related to electric field due to a dipole at axial and equatorial point. As I told you, they both are important ones. Okay, you need to practice those derivations as well. Okay, the next thing is, the next topic that we are going to see is torque experienced by a dipole when it is placed in external electric field. Meaning, in the previous cases, we saw a dipole and we saw how the electric field is generated due to the dipole. Now here what is happening is, if you read the topic, you have a uniform electric field already present. In that uniform electric field, if you place an electric dipole, then how is it going to respond? Am I clear? So having said that, let's see what will happen is, first of all, let's try to come in the reverse, right? So first we need to understand what a uniform electric field means. Yeah. So let's see what a uniform electric field means, right? So just to give you a differentiation, if I take a positive charge, and due to the positive charge, what will happen? The electric field is going to be in outward direction. So how is it going to be? We know that when we draw the field lines, it is going to look something like this. The question is this a uniform or a non-uniform field? This is a non-uniform field. Why is it non-uniform? Because the electric field at every distance is not a constant. In the sense, you know that due to a point charge, what is going to be the electric field at a distance r from it? It is going to be kq divided by r square, where r is the distance from the charge to the point where we are trying to calculate the field, right? So the value of r keeps changing, electric field also keeps changing, right? Yeah. So when this is going to happen, this will be considered as a non-uniform electric field, because if it has to be uniform, it has to be uniform in terms of direction as well as magnitude. So for that field to be uniform, what we need to do is we need to take the set of parallel lines, right? So the set of these parallel lines is what is going to be uniform electric field, in which we have taken a dipole and placed it. So what does a dipole consist of? It consists of a positive charge Q and a negative charge Q here, right? And tell me one thing, in the presence of electric field, what will be the direction in which the positive charge would experience a force? See, let's recollect this concept. We know that electric field is equal to F divided by Q. See, Q naught, I'm keeping it aside. Q can be any charge which you are placing in the external electric field. Okay. So what is going to be the force experienced by the charge? F will be equal to Q into E. So one thing that is to be understood is force is a vector quantity. Electric field is also a vector quantity. So can I say that they both will have the direction in such a way that if the charge is positive, then force and electric field will be in the same direction. If the charge is negative, what will happen? You will have minus of E vector, means the force and the electric field will be in the opposite direction. Is this point registered in your mind? This is a very, very, very important point. Meaning, going forward, wherever you place a positive charge in the presence of electric field, what will happen? The force will be experienced in the direction of electric field itself. Meaning, this charge will experience a force in this direction of magnitude Q into E. I wrote magnitude because arrow mark is drawn. Similarly, the negative charge would experience a force in this direction where it is going to be Q into E. Am I clear with this? No. There are two questions to be answered. So in the uniform electric field, we know that a dipole is placed. This is what is going to happen. But if you see the prelude, right, or the prefix, I will say they're saying it is experiencing a torque. Right. So two things that we need to understand is, if there is an unbalanced force, I repeat, if there is an unbalanced force, the system will move in a translatory path. The system will move in a linear path. Whereas if there is an unbalanced torque, it will start rotating. So torque is responsible for rotation and force is responsible for translatory motion. Having said that, I'm going to answer two questions here. First thing is, what is the net force experienced by the system? So if I write F net, what is going to be the answer? It is going to be QE, which is in the rightward direction, plus negative of QE, which is in the leftward direction. Summing up both these things together will give an answer of 0. Meaning, the system is not going to move. Move in which path? In a linear path. It will either move in this direction or this direction. But what is going to happen here is, this force has a tendency to put the object into rotation. Similarly, this force also has a tendency to put the object into rotation. Meaning, if I take the charges to be like this, if this is plus Q and this is minus Q, the plus Q is being pushed in this direction. So are you able to visualize? The plus Q is being pushed in this direction and minus Q is being pushed in this direction. So what is happening? This force and this force put together, they are making the system rotate. So whenever the system has to rotate, there needs to be an unbalanced torque. So that's what we need to find. Okay. The only thing is, we are going to find the torque in this scenario in terms of the dipole moment and the distances. Okay. So in terms of dipole moment and the electric field. Let's see how it comes. Okay. See, for this system, the center is exactly going to be here. Correct. So if this is revolving, then it should revolve about this axis, about an axis passing through the center itself. Right? 1 minute. Maybe. Those who are online are able to see whatever I'm showing. Is it better now? Can someone respond, please? Yeah.
Yes.
So what I'm saying is, the system is going to revolve about this axis of rotation. In which direction? In this scenario, it revolves in the clockwise direction. Right? So one thing that we need to understand is, see, this is a point which I'm recollecting or revising from your 11th standard. So there are two kinds of moments. Moment is another name given for torque. We call it as a clockwise moment and an anti-clockwise moment, which I want you to visualize. Let's take this water bottle as an example. Right? If you want to open this water bottle, what are we going to do? See, by default, even without your knowledge, you're not going to apply any science or anything. Without any knowledge, you will hold it at both the ends, just turn it like this. Have you ever seen anyone doing like this? Unless it is loose enough, right? I'm talking about the cap. Okay? Unless it is loose enough that like you cannot rotate it like this. Whereas if it is, however tight it is, you're going to rotate only in this direction. So if you see the direction in which this water bottle or any water bottle in this world is opened is universal, right? There'll be no water bottle where you will turn right-hand side and the cap comes up. It is always like this. So when you do this, first thing is you need to see from the top. When you see from the top, when you turn it like this, right? How is the cap coming? Is it coming towards you or away from you? Towards you. So it is revolving in. So anti-clockwise moments and anything measured towards you is positive. So anti-clockwise moments are considered to be positive, meaning if a system is rotating in anti-clockwise direction, it is considered to be positive. Whereas when you want to close it, when you see from the top, you rotate it in the anti-clockwise direction. Sorry, you rotate it in the clockwise direction. So clockwise is away from you. So clockwise and anything away from you is considered to be negative. So that is why clockwise moments are negative. That is a concept we are going to apply here. Okay. In the last step, I'll be asking an important question. So concentrate and listen to this completely. Am I clear till this point? Right. So what did I say? Clockwise moments are negative. Away from you is negative. Anti-clockwise is positive. I hope it is clear. Right. Have this in your mind. This is just an idea to be kept in our mind. Now, having said this, shall we start with the main derivation? So we understood that it does not have translatory motion. Then who's contributing to the rotational motion is what we are going to see. Shall we start? See, if this is going to be the axis of rotation, from this axis of rotation, if you see the perpendicular distance, how much is it going to be? Like this is the point of application of force. If I take this angle to be theta, right, we know that this distance is 2a. It is going to be a. Right? Then how much is this going to be? If I take this to be y, for instance, y divided by a is sine theta. So y by a is sine theta, then y will be equal to a sine theta, and this is going to be a cos theta. In a similar way, if I take this distance and drop it here, then this angle will also be theta, right? This is going to be a cos theta, and this is going to be a sine theta. Right? Am I clear with this? No. The next question is, this force is acting at a perpendicular distance of how much value? So torque, when you write it, no, because you are talking about the torque. So torque, when it is written in the vector form, you write it as r vector cross f vector. The order is very important in the cross product of vectors because a cross b is not the same as b cross a. Right? We know this. Similarly, when you write the same thing in the scalar form, you write it as force into perpendicular distance. I repeat, this is into, not cross. It is force into perpendicular distance. From where? From the point of application to the axis of rotation. So force into perpendicular distance. Whenever you speak about distance, right, throughout your physics or math, you always need to speak about a reference point or a reference line. So here, perpendicular distance from where? From the point of application of force to the axis of rotation, right? So having said this, what is going to be the force? This QE has a tendency to act at a distance of, this QE is acting at a distance of a sine theta. Am I clear with this? Right. Now the questions. This torque, I've written it in the scalar form, but we know that torque is a vector quantity. So if I put a vector symbol on top of it, then it's my responsibility to write the direction. Now you tell me, this QE will make the whole system rotate in clockwise direction or anti-clockwise direction. This is how the charge is. This is how the system is. One force is acting in this direction. So if I push it here and the other force is supporting it, right? In which direction is it rotating according to you? It is clockwise. Clockwise moments are negative. They are away from you, right? So if you take this to be the x-axis and y-axis, what is the direction in which torque is acting in this case? In the negative z-axis. I repeat it. This is taken as x-axis. This is taken as y-axis. Anything towards you is positive z, away from you is negative z by default, right? So if I take that to be the scenario, in which direction is the system revolving? Clockwise. So what will be the direction of torque? Into the plane. Into the plane is considered to be negative of z-axis. So what is the unit vector used for negative of z? Minus k cap. Makes sense? Right. So this is the torque that is acting due to the positive charge. So what about the torque that is acting due to the negative charge? It is QE into force into, so it's a force into perpendicular distance. So force is again QE. You should not take minus QE because you have already assigned the direction. So QE into A sin theta, right? So this torque, if I write it in the vector form, what will happen? This is also making the system revolve in the clockwise direction. So it is going to be negative of k cap. So unlike the force, which was in positive x direction and negative x direction, which got nullified, torque is not getting nullified because both the torques are acting in the same direction. So the net torque, when you write it, right? So it is going to be the torque due to the positive charge plus the torque due to the, 1 minute. So it's going to be the torque due to the negative charge. So what is the torque due to the positive charge and negative charge summing up to? It is QE into A sin theta plus A sin theta, which is going to be 2A sin theta, which is going to be in the negative direction of A. Right? Now it's simple. What is this Q into 2A? It is P into E. Right? So this is P into E, and you're left out with a sin theta and negative of K cap, which is going to be the net torque that is experienced. So this is the torque that we are trying to answer. But here comes an important question. Every time you cannot write it as P sin theta minus K cap. You need to write it in this form, like how you wrote torque as a general formula, R vector cross F vector. Here you need to write the relation between P and E. So with respect to cross product, there is a challenge. What is it? A cross B is not the same as B cross A. So this is where we need to think whether I should write it as P cross E or E cross B. Had I left it normally, right, you would have told it is P vector cross E vector because I wrote P first and E next. If I write EP sin theta, then you will say E vector cross P vector. But one of them is correct. So which one should I write? For that, we need to think about it. So if I take this to be the dipole, what is the direction of dipole moment? Because one of the vectors involved is dipole moment. I need to know the direction of dipole moment, which is P vector. Am I right? It is from the negative to the positive charge. That's what the basic says. Right? So listen to this carefully. 1 minute. Can you give me your pen? Yeah. See, if suppose, can I have another pen, please? See, if suppose the system is like this, right? When the system is in this way, where I call this as A vector and this as B vector, right? If I do A vector cross B vector, I need to keep the direction of the first vector fixed. In A vector cross B vector, which is first, obviously the one before the cross, which is A vector. I need to keep the direction of it fixed and turn, you need to keep the direction of the second vector fixed, which is B vector, and take the first vector and turn it towards the second vector in the shortest direction possible. This is an important point to be noted. So A vector plus B vector means fix the position of B. It's here. Now this A vector has to reach this B vector. It can reach in two directions. I can reach it Either rotate it like this means with respect to you, it is anti-clockwise direction, or I can rotate it in clockwise direction also. But which one is correct? I need to rotate it in the shortest possible direction. Means I need to rotate it in the anti-clockwise direction. When I do that, you get an anti-clockwise moment. So what do you achieve? You achieve a positive value because anti-clockwise moments are positive. Suppose I do B vector cross A vector. The second vector should be fixed. B vector cross A vector. Second vector should be fixed. First vector should be rotated towards the second vector in the shortest direction possible. When you rotate it, it revolves in the clockwise direction. Hence, you get a negative K, right? So, having the same thing in mind, what we will do is, if I take P vector and E vector, this is P vector. E vector is like this. Make sense? So, if I write P cross E, what will be the direction of torque? If I write E cross P, what will be the direction of torque? So, use the same logic. If I write P cross E, I need to fix the position of second vector. E vector is fixed. From the first vector, I need to turn towards the second vector in the shortest direction. So, which direction will I rotate it? When I rotate it clockwise, what is going to be the moment? Is it going to be positive or negative? In this case, what did we get? So, it's satisfied. So, that is the reason why the torque net, when it is written in the vector form, is written as P vector cross E vector and not as E vector cross P vector. See, this is a very simple point. In your textbook, they would have told, accept it. But I wanted you to visualize why this is happening because you need to understand the basics of cross product. You will see this concept in your math also in a chapter called vector algebra. So at that point, you should not again learn it. Okay, it's very simple. Is that clear? So this is all about the torque experienced by a dipole placed in uniform electric field. Now listen to this question. So this is the topic. Now the question is, if I change the uniform electric field to non-uniform electric field, what do you think would have happened? If I change the uniform electric field to a non-uniform electric field, what do you think would have been the answer? Would change. Okay. Anything else that would have happened, which didn't happen in this case? You think of the logic, right? This QE and minus QE got nullified only because they are exactly acting along the x direction and the negative x direction because of the uniform electric field. Had it been non-uniform, this force would have not had a confined direction. Meaning, the net force in the case of a non-uniform electric field would have not been 0. Meaning, there would be torque. In addition to torque, there would also be force. So, if you visualize it, in this scenario, this object is only revolving like this, about a fixed position. You can imagine the minute hand of a clock. So, it is revolving about a fixed position. It is hinged at the center. So, it will keep revolving like this. Whereas, if the same system was placed in non-uniform electric field, the system would have rotated as well as had a translatory motion like this. Means it moves like this, right? It will keep rotating as well as moving, but we don't know in which direction it will be because it has a non-uniform, it has a non-zero force. So force plus this one will give a combined rotation and a translatory motion. Am I clear with this? Right. So as I told you, this is a topic in your textbook. Now you can make a note of it. Yes, ma'am. Dipole moment is available. It's something like you need to know the direction in which that is acting. No? They have assigned it like that. They have assigned it like that. That's it. It's multiplication of two things. As I told you, this has a lot of application in your chemistry. So there you would have learned bond moment and everything. It's the same logic there. You will say when you take a HCl molecule, what will happen? You speak in terms of electronegativity and electropositivity. One one is going to have a slightly positive charge. See, H plus, Cl minus. In terms of H plus and Cl minus, in terms of it, both have got combined to give you the molecule of HCl. So they have the same amount of positive charge also. But is are they present in such a way that the whole charge on H plus is only H plus, or Cl minus is Cl minus is the question? Meaning, there will be a slight bond shift, right? The electron pair is there, no, which has participated, and the electron in the shift. So adhanal in the side light or positive charge irukma delta plus. The delta plus is what is Q. This is delta minus. So adhanal what will happen is there will be a small moment that is existing. That there is something like this that is observed. Adukku per dhan dipole moment nu sonna. So the dipole moment, if it has to have a direction, they have assigned it saying that it is from the negative to the positive. See, some things are assigned only to make your make things simple. If electric field, somebody who defined it first, right? I'm saying electric field due to a positive charge is away from it. Maybe had I invented, if I have the negative charge to be my favorite charge, I would have told electric field due to a positive charge is always towards it. I would have told test charge is negative. And the invent pannavanga, what they did is Q naught, by default, they told it is positive. Why should it be positive? Na negative when I invented it. So something like that, dipole moment, when it was found out, it was given this direction. That's as simple as that. Okay. There is no specific reason why this is happening. Because the QE will put the charge into which rotation? This QE will make the system rotate in the clockwise direction. No? Give me a pen, no, 1 minute. This is there. This is the direction of QE. QE. So when I apply force like this, see which direction it is rotating. So here I apply a supporting force. It's rotating the clockwise direction. So when it is rotating clockwise, it's a clockwise moment. That's why minus K. Where did they take K cap? When will it be K cap? Reverse the direction. Take positive charge here, negative charge. It is, I'm not saying it is moving into Z axis. I'm saying the torque is acting in the Z direction. That's what the screw rule says. No, that's what I showed you with the bottle. When you rotate it, actually you're rotating it clockwise. But how is it moving? It is moving into the plane, right? That is the same logic. Done? So, is everyone done? You're copying. Copy. Okay. Done? Okay. So we need to make a note of the point that I mentioned. What did I tell you? So the point to be noted here is, if the dipole was placed in non-uniform electric field, it would experience both force and torque, right? It would experience both force and torque, meaning the system will have a combined rotational and translational motion. So to put it simple, you will have a rotational plus translational motion. Yeah. So I just wanted to show something. Any idea where this concept will be applicable? Are you able to guess? Ball going down is due to gravity, right? I'm not saying you're talking about rolling motion. Rolling motion is the mechanical force. It's not mechanical force. Motor. Just give me a minute. Just give me a minute. Okay. Myself, I'll tell you, I thought I'll show you something, but it's not working. Anybody who's online, can you guess where this will be applicable? See, if you take an oven, right, microwave oven, is that what you told? No, right? Okay. If you take a microwave oven, we place some food item only for 20 to 30 seconds. You take, for that matter, popcorn also, right? When you place it, it gets popped up, right? So how is it happening? Because every food item will have some water molecules present. We know that water is a dipole. And what is present inside a microwave oven? You have electromagnetic waves. We call it as EM waves. That is why they say you're not supposed to have a lot of microwave food also, right? So when you have this electromagnetic waves, electric field is generally dominating in the case of electromagnetic waves, right? So in the presence of an electric field, which is non-uniform, if you try to cook food, right, you can see that the boiling or it gets heated up faster because of this combination. What will happen is the food particles will experience both translational and rotational motion, and they get collided. Right? They start colliding with each other in such a way that the heat is generated faster. So there's a real-time application. You're able to understand. So that's what happens. If you see the value of electric field inside it and all, it will be very, very, very high. Right? So there's one of the applications of this concept. Right? This is clear. Shall we go to the next topic? So we are almost about to complete this chapter. The major topics are over. Right? I hope you're able to understand. I'm going as slow as possible, actually. Right? So the next concept that we are going to see is electric flux. 1 minute. The pencil is here. You're able to see any pencil there? Okay. Listen. So the next topic that we are going to discuss is electric flux. Okay. So this electric flux has something to do with the density of field lines. It has a significance. Okay, I'll tell you where it is useful in physics. See, if you take the same example of this positive charge, due to this positive charge, how will the electric field be? These are the field lines. Am I right? So when you take these field lines, right? Now, when you take these field lines, you're able to see that it is more crowded near the charge, and as you move away from the charge, right, you can see that the distance between them is increasing. When I talk about a non-uniform electric field, right? Meaning, if there are field lines, if I take an area here, means if I take my hand and place it like this here, I'm able to see that 3 lines are passing. Whereas if I take the same and keep it here, I'm able to see only 1 line passing. Means as I move away from it, I'm able to see that the number of field lines that are passing through the area that we have considered is changing. Right? So it has a significance. So instead of using the word like field line density, if we call it as flux, right? This flux will tell us what is the strength of the electric field generated due to a system of charge at a particular place. So that is the main objective of it. For that, which we need to understand what is the definition of it. So if you see, electric flux is basically the total number of field lines of force. These are the field lines of force. If you calculate the total number of field lines of force that are passing through a given area, the area is the finger that I consider. Right? If you're able to calculate the number of field lines that are passing through the given area that you considered, but a point to be added here is through a given area, perpendicular to it. Means for this area, you need to take only those lines into consideration, into the count, which are perpendicular to this area. Are you able to understand what I'm trying to say? Right? So that's what electric flux is all about. Right? So when you calculate the electric flux, right? See, if I take this to be the area, and let's say this is the way the electric field lines are there. I have taken a consolidated value of the strength of all those electric field lines through this area as one vector, and I give a name to it called as E. Right. So what is that we are suggesting? So for you to define the electric flux, you need to calculate the total number of field lines that are passing through the given area perpendicular to it. Meaning this electric field line is supposed to be perpendicular to the area. So the shape is like this. Right. The shape is in this way. This is the direction perpendicular to it, but the electric field is like this, right? So if I take this angle to be theta, right? Now there is a point to be noted that for any surface, when you talk about a two-dimensional surface or a three-dimensional surface, the area that you have considered is always perpendicular to the surface. How is it? It is perpendicular to the surface. And the next point to be noted is in the outward direction. In the outward direction. Okay, I'll tell you what is the meaning of that outward in the case of 3D. So as of now, you're able to see, the circle is there. I've considered the aerial vector to be perpendicular to the surface. So this is going to be the direction of area. So electric field and area, they are acting at an angle of theta with respect to each other. Now this electric field can be resolved into two components. One is E cos theta and the other is going to be E sin theta. If you see, E sin theta is not a component which is perpendicular to the surface. Only E cos theta is perpendicular. So if you are able to take the product of this E cos theta and A, then this is going to give me the flux. Right? So if you write this flux, this will be equal to E vector dot A vector, and this is read as phi. Okay. So this is the mathematical symbol for flux as such, right? So if you put phi with the subscript E, you call it as electric flux. Because the same concept we'll be discussing magnetism also. There we call it as magnetic flux. Right? If whatever you are able to understand from here is the same thing applicable there also. Now, I told you that aerial vector is perpendicular to the surface in the outward direction, right? What is the meaning of it is, if I take this cube, then this side is there, no? So that side is going to be a, okay, there's a cuboid. So that side is going to be a rectangle, right? For that rectangle, I can define the aerial vector perpendicular to it in either this direction or in this direction. But which one should I take into consideration according to physics? I need to take only the rightward one because it says the aerial vector is always in the outward direction perpendicular to the surface. This is a very, very, very important point to be noted because this is what we use to solve problems. There are two important problems in your textbook, which when I discuss that, right, you'll understand this thing better. But I want you to remember this point. What is it? Can you please state it? Aerial vector is always in the outward direction perpendicular to the surface, right? So please make a note of this. 1 minute, 1 minute. So I wrote the mathematical expression for flux, right? Now, what kind of a physical quantity is this? Is this a scalar or a vector? It's a scalar quantity because you're talking about the number of field lines. And one more thing is it's a dot product. It's a scalar quantity. Now, what is going to be the SI unit for it? This is Newton per Coulomb. And this is meter square. So it is going to be, I'll write it clearly. What is going to be the unit? It is going to be Newton meter square per Coulomb. Am I clear with this? So now we can make a note of this. Yeah. So yeah, this is all about electric flux. The few more topics that are pending is, till now we were discussing about the point charge, right? But it is not necessary that always the system will be a point charge. It can be an extended charge. So like, see, you can think of your pen getting charged. If you take your pen, right, it is a linear charge where you have everything getting charged. If you consider it to be a cylinder, then it will be a three-dimensional charge. So those are all called as extended charges. So I'll just give you a brief of what we are going to discuss next. Okay, just give me a minute before you copy this. So we'll be discussing about this thing. One is charge distribution, where there are three types: linear, surface, and the volume ones. After this, we'll be going to an important law called as the Gauss law. Right? Gauss law is something like a substitute for Coulomb's law. Meaning Coulomb's law is applicable only for point charges, right? What if we have extended charges? You can apply Coulomb's law. I'm not saying you cannot do it, but it's a complicated process because you need to apply a little bit of math. Like you need to consider a small charge and integrate and all those things, which is not a part of the syllabus. So if you're for competitive exam, you can learn that. For CBSE, it's not there. So as a substitute of it, what they did is this Gauss law is proposed, right? So this Gauss law has three important applications, which is for an infinitely long state charged wire. Then we'll see for an infinite plane sheet and for a uniformly charged spherical sheet. So for all these things, what I've done is, even before we apply, see, this is something which I prepared with. This will not be available. I've prepared the algorithm, like the flow chart of how you are supposed to apply this Gauss law to any concept. Though they have given only 3 in the textbook, this concept, if you follow, you can apply it for anything. There are 7 steps, okay, which I will teach in the next class. So max, I don't think we can complete it by tomorrow. And I don't think we are in that urgency also. So by Monday, I'll complete. Okay, that is one thing. There are some topics, right, which I could understand from your faces, or some faces which are at the back. Like sometimes you're feeling sleepy, I understand. One is climate is like that, and the topics are also slightly dry, right? So for those things, what I'll do is I'll give you pre-recorded videos, which will not be more than 15 to 20 minutes. I'll consolidate, condense everything and give it to you so that you can go through it multiple times. Before the class itself, I'll tell you. So for those topics, go through the concept, come here, so that I'll touch up on it once. So I will brush it up once, maybe for 5 to 10 minutes. Then we'll do some problems, right? See, the major problem is with your question paper that has been changed. I see most of them struggling not with the concepts, with MCQs, assertion reason based questions, and the case study based questions. So I want to cut that faster. If that has to happen, we have to follow this process from the beginning. So it has only been 1.5 weeks, right? So slowly what I'll do is I'm actually working on the pre-recorded versions also with better clarity. I'll record them and give it to you wherever the topics are big and time consuming, which I don't want to waste in the class. We get only 3 hours, no? So I need your cooperation in going through them and come. Please don't come up with any excuses because I'm also working along with you. Right? It is for you guys. So don't give any excuses. Don't say I don't have time or anything. Monday you're coming to class. Sunday at least spend 30 minutes for that. Take notes and then come. Be sincere. Okay. So that we can concentrate on the problems, because I didn't do problems this year. You see, I've been only teaching, right? I didn't tell you how to apply the equatorial, the electric field due to the values that we have calculated till now. I have to teach, right? So we need to save time. So this is one thing I wanted to just inform you so that you be mentally prepared. Okay. Anything else that you have in your mind? Any questions? Anything that you have learned but you didn't understand? Is everything clear? Same mass as whom? If at all you ignore the number of electrons that are lost or gained, they have same mass. That's an ideal situation. But speaking in reality, electrons' mass is also taken into consideration, because when you talk about atomic mass, whose mass do you take into consideration? You take only the neutrons and protons into consideration. But in reality, when a material is getting charged, it loses electrons. Electrons also have some mass, right? Though it is a very small value. It's 9.1 into 10 power minus 31 kilogram. Even if one electron is lost, that much mass is lost. So one material is losing that mass, one is gaining that mass. Because it's a small value, ideal situation, we don't take into consideration. Why I'm stressing this much is that depends on the question. So you need to, you need not take, mostly they will not speak about mass. They will not speak because we are concerned only about charge, right? So think about it. Anything else? Fine? Is everything fine? Okay, then shall we wind up? Those who are online, shall we wind up?
Yes, sir.
Okay, I'll see you.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah. Electric? Okay. Phone